The moon's magnetic field should have died 3 billion years ago when the core cooled and solidified. But the billion-year-old moon rocks suggest it didn't.
So the question is, how could the moon have had a magnetic field? And the answer may be that because of tidal forces from the Earth, the moon is being kind of flexed.
When the moon formed, it orbited just 12,000 miles away from the Earth, making it appear 20 times larger in our sky. The moon was so close, Earth's gravity could stretch and flex it. This internal distortion of lunar rock created friction, and friction creates heat.
And it's a lot of friction. It's so much heat dumped into the interior of the moon from this effect that it actually kept the mantle of the moon molten longer than it would have been if it had just been sitting in space.
So it could have prolonged the heating on the internal parts of the moon and extended the time that its magnetic field would have survived.
This heat kept the moon's magnetic field alive for an extra 2 billion years. Long enough to imprint the 1 billion-year-old Apollo 15 rocks with a magnetic field. But over time, as the moon moved away from the Earth, the friction heating dropped. The lunar core cooled.
When the moon was closer, this effect was very, very strong. Nowadays, the moon is far enough away that that effect is too weak to keep the mantle molten.
Eventually, the moon lost its magnetic field when it stopped being so liquid and gooey on the inside. Once it solidifies, once it cools, there's no more movement, and so the magnetic field just falls apart.
When the moon lost its magnetic shielding, it flatlined. The solar wind bombarded the lunar surface, leaving the moon a radiation-scorched wasteland. A dead world orbiting the living Earth. Or so we thought.
In a general sense, it's okay to say the moon is dead. It's just kind of sitting there. What you see is what you get. However, the Apollo astronauts left seismometers on the moon, and what they found is that it's only mostly dead.
Powerful forces are stirring on the moon. The lunar surface is shaking, giving rise to vast new rocky structures. Could our cosmic twin be coming back to life? The moon's surface carries a record of its history. The scars of asteroid impacts show that it hasn't been active for many years. But scans of the Schrödinger Basin tell a different story. They show recently formed rocky ridges free of large craters.
The moon appears to have been dead for a long time, and we can tell because it's scarred by all these craters from impacts for the past 4 billion years. But there's some features on the moon that are free from craters, which means they're relatively young. So how can a dead world have a new young feature?
These young features are called lobate scarps.
They're faults in the moon's crust that are formed by two pieces of crust coming together and sort of one riding over the top of the other.
These scarps can be tens of miles long and hundreds of feet high. Something powerful is creating these rock formations. But what? The answer could be found in a decades-old lunar mystery: moonquakes.
Just as the Earth has earthquakes, the moon, we know, also has moonquakes.
Apollo astronauts left seismometers on the moon to measure moonquakes. And they got some, and that's not terribly surprising because without an atmosphere, any little bit of rock out in space that slams into the moon's surface, it's gonna hit and create a shock wave which will be picked up by the seismometers. But they also picked up something that wasn't from asteroid impacts. It turns out those were true moonquakes.
Over an 8-year period, the Apollo missions recorded more than 13,000 tremors. 28 of these were mysterious true moonquakes, measuring up to 5 on the Richter scale. These moonquakes can't be explained by events on the lunar surface. But what about underneath it?
Given how small the moon is, you would imagine that it cooled off long ago and it's just an inert rock doing nothing. But something is happening under the surface of the moon. The moon may not be as dead as we thought.
On Earth, our planet's hot interior drives tectonic activity and triggers earthquakes. So, could the moon's interior still move like the Earth's?
Probably the most common mechanism that generates earthquakes is the slipping of our tectonic plates, the cracked crust of the Earth. They don't slide and glide evenly. They get hung up on each other because of friction, and the stresses build, and over time that frictional force will give way and there'll be a slippage in the plate.
And for that to work, you have to have a real active tectonic system where things are colliding and moving around. You need a liquid mantle that allows this sort of movement.
When we use the Apollo seismometer data to look for a liquid mantle in the moon, we were in for a surprise. The moon's crust is made of solid rock that extends 600 miles beneath the lunar surface. It's 20 times thicker than the Earth's solid crust.
On the moon, there's no crust floating over sort of a liquid mantle. So without that, you're not getting the same sort of tectonic activity that you do on the Earth.
Without a liquid molten mantle, true moonquakes can last for over 10 minutes, many times longer than quakes here on Earth.
On the Earth, we've got plenty of things to absorb all that energy from earthquakes. We've got liquid mantle or molten mantle, liquid oceans, a lot of shock absorbers. On the moon, big solid rock that's more or less dry as a bone. That energy can just ring and ring and ring and continue for a long time.
Moonquakes last a lot longer than earthquakes simply because the interior of the moon is mostly rigid and dense. It's dense all the way down to about 600 miles, whereas on Earth, we start getting sort of gushier material at about 100 miles deep. So if you have 600 miles of rigid material, then the waves can be transmitted through that really efficiently.
Earth-like tectonic activity didn't trigger the moonquakes, so we looked for something else. By triangulating the tremor's epicenter, we discovered that they originated around 15 miles underground. And one of the quakes happened near the Schrödinger Basin, where we found the lobate scarp ridges.
The lobate scarps are evidence probably of the sources of the shallow moonquakes that we're detecting with the lunar seismometers left by the Apollo missions.
Let's put the evidence together. Something formed the lobate scarps, set off giant moonquakes, and it's happening inside solid rock.
How in the world is that possible? It turns out the moon is shrinking. It's shrinking as it cools.
If you take something that's cooling like that, it's going to try to shrink. And the surface of the moon is shrinking, but it can't. It can't physically shrink. It puts it under too much pressure, and at some point, it's going to snap. And that's where we think these scarps are coming from. And if you create a scarp like that, you're gonna get moonquakes.
The new ridges and moonquakes aren't the signs of a healthy, tectonically active world. They're the moon's death rattle.